Okay, so what are a couple of options we could have put on there?
Waiting time.
Okay, waiting time. So how long they've been waiting? Fair enough. Go ahead.
How much time it needs in the CPU?
Okay, so it could be turnaround time if we're able to predict that, or just even in general, we could just say, how long will it take to complete? Can we kind of get this finished quick? If so, well, let's go ahead and take care of it, especially if it's been waiting for a long time. Anything else?
If it's going to be IO heavy or not. So it kind of rolls into waiting time.
Sure, that's fair enough. Yeah, I mean, and that kind of goes into, is this something we can handle quickly, or maybe even the other way around? If it's going to be I/O heavy, is it going to spend very much time on the CPU? Are we willing to roll the dice on the context switch just to get it on there, to get it back in the waiting queue? So now, technically, it's not starving because it got CPU time. And then it immediately said it kind of rejected the CPU time because it needed to go do something else. Okay, now his starvation clock starts over. All right. Anything else?
Would it look at what type of processes, like kernel thread or IO? Or
user process that needs to seem happy?
Possibly. I mean, that would really be more of a the long-term scheduler getting it into the right queue. Yeah, but well, I mean, I'm trying to think, just outside of the box a little bit. Is it possible that the short-term scheduler might take that into consideration? I mean, the punchline is there's a whole lot of reasonable answers, right? I don't think that's unreasonable. Let's try to make a determination who's in the system, and should they get the CPU time next and why. We're going to use more than just priority, so maybe their stature in the system. So that could be construed as kind of priority, but even within priority, if it's a kernel level thing, maybe we're going to kind of say, well, we definitely don't want to starve the kernel. We want the user to be faked out and happy and all that stuff, but if the kernel wants to do something, there's probably a good reason for it. Fair enough. Anything else? Go ahead.
Loeffler just let all of his students out of his class.
What? What fun is that?
I mean,
Cafeteria doesn't open for 45 minutes. What am I supposed to do?
By the
Let's
way,
go fishing.
I did go fishing yesterday.
did you catch anything?
No, I even trolled. It was so cold. So I even trolled the crank. I think the fish are all dead.
You thought that last time I went out.
No, I got you. I literally trolled for what 2 miles, whatever the from the dam all the way back to the dock.
Were you running that that rattle crank?
Yeah, I was running the crankbait, but I just
green?
trolled it.
Was it? Oh, you just trolled it?
I trolled it for 2 miles and didn't get a hit. Nothing.
Well,
I should have. Well, I was listening to my audiobooks. It actually wasn't bad.
Is it a deep water?
About 8 feet at the deepest.
They're all really deep right now.
Well, they're really deep in Milwaukee River is max 8 feet.
Yeah,
at least where I go.
About 4 feet last time we were out there. That was like a week ago.
And there was some floating ice on top.
Yeah.
The water.
Okay, that might be a little different now. Yeah, the water was a little warmer.
The motor started right up.
Hey, told you, fixed it.
We'll see.
get
So
out
that means as soon as it doesn't work again, I can blame it on you too.
Only if I take the boat out.
All right. So last time. So he let him out already?
Yeah, that's what I was thinking too. I was like, wow, that never happened for me.
Pretty pissed that I had to show up for class.
Right? I'd be mad I wasted the gas.
Seriously.
Like,
Man,
that's
what?
why you let him out. There was no one there.
I got physical therapy.
Well, but I mean, there's probably a high skip rate in his classes anyways. I mean, who can sit there and listen to that for 50 minutes?
It's hard.
It was only like 6 or 7 people.
Wait, that's our recording.
All right. I mean, the good news is I won't give you. Well, maybe I should now
No,
give you homework over break.
I'll break your boat.
I just think maybe now I should.
Well, I don't know. There was complaining about why aren't I letting you out of class
Oh,
early?
no, I was
No.
complaining like that.
It was just-
I just said Loeffler let his
All right.
Yeah.
I won't give you homework over break. I thought about it,
Oh,
but I decided I didn't want to have to grade it. So I still have to catch up another. Actually, I think I'm caught up in here. I think all the assignments are caught up in here. have a couple other classes I need to catch up with. Okay, so we were talking about some, we talked about starvation last time, but then we started talking about specifically, actually a very, very poignant conversation on Thanksgiving week, starvation, right? All right, so in any case, we talked about some various scheduling algorithms that we can generically apply to our queue. So, we had several different things we talked about here. Where it is. Yeah, we had first come, first serve, shortest job first. And we talked about kind of the challenge with that is it's difficult to predict how long a job might actually take. But what we can use is we can gather statistics over the runtime of the operating system. For example, like I think I mentioned last time, I have several applications on here that have been, I don't remember when I opened them. They've been open for weeks. Very much a laptop world type thing, right? We never shut down our computer, and even desktops, and we don't shut down our desktops very often either, unless you're just really pinching pennies on the power.
I restart my laptop every day.
Really? Well, you're an idiot.
Better for it.
What do you mean better for it? How is it better for it?
Lets it cool down.
You shut the lid, it goes into sleep mode.
Well, I play Fallout on it. Fallout 4 on it. It needs to cool down.
So you shut the lid, and it's just as if it's off. Doesn't make any sense to restart it.
Power going into it.
Doesn't make any sense. In this case, you're completely wrong. There's a 100% chance that you're wrong in this case. If you close the laptop, the battery is still charging, but the processor's not running. None of these things are happening. That's Apple last year, released their what's called the power nap. Their stupid thing where it pops on real quick to check your email, then pops off. Stupid, just to keep your stuff kind of up to date. But the punchline is, if you shut the lid to your laptop, your machine's not going to overheat. The machine is off.
And I'm also paranoid.
Oh, well, that's a whole other problem. It has nothing to do with heat. Huh?
Unless you're running Windows.
Yeah, I mean, if you
occasionally it might.
Yeah, you might
put my laptop.
I'd say it actually probably is
It's been
just.
hot.
Yeah, I was about to say,
it didn't hibernate correctly.
Yeah.
yeah, I'd probably say it is more of a habit from when I had Windows machines.
Well, see, now he's just backpedaling. All right, so shortest job first, we decided might be difficult, but what we can do, especially in today's world, is we can gather statistics about applications that maybe have been open for a long period of time. And we can say, okay, well, on average, the Xcode processes, let's say, spend X amount of time, Christian worldview, X amount of time on the CPU. Therefore, we can make a judgment, a guess as to how long that job is likely to spend on the CPU. Okay? And if we can, so for instance, things like that, which maybe have quite a bit of user I/O, especially when you're doing the actual development, you're constantly interacting with the process. That might be something that we only give highest priority to if it's in the foreground. Right? We don't really want to give it much CPU time if it's in the background. We don't care how sluggish Xcode gets if the person's not paying attention to it. That type of thing. So we can gather some statistics of actual usage of our machine and adapt to that based on the shortest job first type approach. Next length of next CPU burst. So this is kind of we're going to give priority to things that are probably not going to context switch onto the CPU, then immediately context switch off. If we can put something on the CPU and make a lot of progress for its entire time, that might be a fairly high, that might be a good choice for what gets the CPU time next. Something that's going to use the CPU time most efficiently. Something like that, assuming there's not something else that is more pressing, even if it's less efficient. Shortest remaining time first. Again, this is kind of if we can determine if that something is running to completion, but that makes less and less sense today in a batch processing type system where you basically have a whole bunch of stuff that is loaded in, is going to run from start to finish is when it gets CPU time, and when it's done, it's done. Not a whole lot of user interaction. It's just number crunching stuff. This maybe makes the most sense. Let's just, whatever we can finish soonest, let's just go ahead and get it out of the system. All right. But in a general user type operating system, shortest remaining time first probably doesn't make tons of sense. Humans are too unpredictable, and the types of tasks we're running on their operating system don't complete, right? When you have instant messenger open or email open, you have it open because you get new emails every single day or every single hour and, often. So you keep it open, you keep checking it. That thing may not end until you actually reboot your computer or it restarts for a software update or something like that. Okay, so priority scheduling, this is kind of, the thing we initially proposed is this might make some sense. And at first, all of our modern scheduling algorithms are going to be based on priority at some level. Okay, so priority is a good first stab at it. Let's decide which things are clearly more important than other things if we can. So let's at least stage our PCBs in such a way that they're presented to us in highest priority order. Okay? Then from there, we can decide what makes the most sense. And we kind of talked about two approaches to this, preemptive or non-preemptive, for how these guys utilize the CPU and lead the CPU. Problems with priority scheduling directly is starvation, and then one of the proposed solutions was aging, right? Where we just kind of its priority bumps as it gets older, so then it's likely to get picked, off the higher priority queue. Okay, so I think kind of where we left off was this idea of round robin. So again, this is kind of a human fairness approach. Okay, so instead of being first come, first serve, if human beings can drop back a second and say, okay, well, the CPU is really fast, we're all going to get to put our order in, if we're at McDonald's. But instead of putting our entire order in at once, we get to order one burger at a time. Or something like that. And they're just going to keep whipping through the line over and over and over again until we finally spit out our entire order. And as long as the CPU, the person taking your order, is fast enough, from our perspective, that might be good enough. Okay? So, generally speaking, human beings are willing to help out others as long as it doesn't negatively impact themselves too much. Right? Okay? We're generous as long as it's not inconvenient, is kind of the punchline. So that's kind of the approach for round robin, is let's get a cadence. So in a completely fair society for round robin, we have 5 things on the CPU, each one's going to get 20% of the CPU time. We're just going to deal with them. You get a little bit, you get a little bit, you get a little bit over and over and over and over again. And sometimes things are going to leave the ready queue because they're going to go and be waiting for I/O or something like that. So then the 4 guys who are left in the ready queue are going to get 25% of the CPU time until somebody jumps back in there.
Even if one was significantly longer than the other one, it wouldn't give it more time.
Not in a flat state. I mean, that would be us adding some additional logic into it. But just pure round robin is going to say we split the time evenly and we just give everybody an amount of CPU time. So each process gets a small unit of CPU time, a time quantum, and usually 10 to 100 milliseconds. But a lot of stuff can happen on a CPU in 10 to 100 milliseconds because they're fast. Okay, so human time doesn't really scale well to even a second. We're sluggish. So humans, mostly, we think about things in terms of minutes, right?
I just farted so bad I made myself gag. Sorry.
I feel like I'm just sitting in front of an 8-year-old.
Only when I'm, probably all the time, but
All right.
more so when I'm on Vicodin.
So stop taking the Vicodin or stop complaining about it.
Well, no, I wasn't. You were complaining.
All right. So in any case, we can accomplish a lot in 10 to 100 milliseconds. After this time has elapsed, the process is preempted, so interrupted, synonyms, okay, and added to the end of the ready queue. All right. So, the idea is that it's going to get its CPU time, and reasons it leaves the CPU is it runs out of its allotted time or it runs out of things to do and doesn't want to delay the CPU. So if there are n processes in the ready queue and the time quantum is q, then each process gets 1 divided by n of the CPU time in chunks of at most q time units at once. So we're going to choose the amount of time each guy gets. So let's just say it's 10 milliseconds. If we have 5 guys, they're each going to get 20% of the CPU time with the maximum individual visit of 10 milliseconds. All right, so if we decide over a minute the amount of CPU time is this, okay, we're going to split that up 20% apiece to the 5 processes, but each time they visit the CPU, they're only going to get 10 milliseconds. So this number right here, the 10 to 100 milliseconds, that's where we're kind of modifying, making a guess at what's enough time to make the end user feel like all their processes are getting CPU love, okay? But that context switching isn't taking over. Okay, so maybe we say 10 milliseconds is too short, that we're going to start feeling the sluggishness from the context switching. Maybe 100 milliseconds is too long, that the user's going to feel like one of their applications is running great, but everything else kind of seems sluggish because, it's getting too much CPU time. That would be hard for us to say without the experience, but if we're actually using the system and we have 5 applications open and one seems good and the other 4 seem sluggish, it's probably because they're not getting enough CPU time often enough. Okay, or at least they're not getting CPU time often enough. All right, so this is a whole balancing act because we have to take into consideration that whole context switching stuff. So the timer interrupts every quantum to schedule the next process. That's assuming that a running process, a job. It's a job when it's on the CPU. It's a PCB when it's sitting in the queue. But whatever, the running process, assuming he doesn't cancel himself, preemptive self, say I'm done. I've gone as far as I can. I need some I/O now. All right. So otherwise, we kick him off the CPU. So kind of ways to measure performance here. If Q is large, so here's our time quantum. That's the amount of time we'll give each guy on the CPU. Okay. Then we might deal with it in a first in, first out. So it's a line, right? First come, first serve, first in, first out. We just kind of round robin it like that. If we're going to keep a relatively small quantum, not give each one very much time on the CPU, so Q must be large with respect to context switch, otherwise overhead is too high. Kind of what we just talked about. All right. So got to find the happy medium there. So as Q gets large, this basically becomes first come, first serve.
It's like two in the car.
Okay. So that's stupid, but I think we understand how round robin works. All right, we don't need to go with their little paint by number pictures. All right, and this guy's all about context switching is expensive. Okay, so we don't need to look at the specific math. We just know that we need to do it, but don't want to do it too often. Good enough. This is a current price of a stock, random stock. It's gone down a little bit.
Like your profile on the app.
That's right.
Did you guys ever fix that bug?
I don't know. I haven't checked. Okay, so multi-level queue. So this, we've already kind of discussed this as it relates to our queues in general, right? That we have a queue of queues in our little simulator that we've written up to this point, where that queue of queues has higher priority queues and lower priority queues. Queue of queues. Huh? Lord of Lords, queue of queues. Christian worldview. Okay, so maybe the ready queue is partitioned into separate queues. So maybe we have a foreground queue and a background queue. So maybe the foreground queue, this is stuff that's, this is taken into a little bit more, a broader level than we already had it at, where these are applications that are actually in the foreground. So we're going to call those most important to the end user. And then we have our stuff that's running in the background that might be important, maybe has its own priority within those, but is stuff that the user is less likely to notice. Okay, so we break our priority down into two global groups. Things the user's likely to notice, things the user probably will never notice, but still might be high priority. Okay? Okay, so each queue has its own scheduling algorithm, so maybe the foreground queue is round robin. Okay, so this is us putting multiple scheduling algorithms into the system. So maybe the foreground is round robin, and we're just going to say anything the user is currently actively interacting with we're going to go ahead and just give each one some CPU time so they feel like they're all getting active CPU time. The background processes, maybe we deal with these on a first come, first serve. Notice they call it batch processing up here. So as things need to happen in the background, we'll just deal with them as they get in line. They'll still have their time quantums. We might even use a different time quantum for those guys. Maybe we give them a little bit more time on the CPU since the user won't maybe necessarily notice. So let's waste less time context switching if the user's not going to be aware and kind of just get through that list. The nice thing on modern computers that have multiple cores is, since it's difficult, we've kind of talked about division of labor. Multiple cores only really helps us if we can really divide a problem up into 4 subsets, right? All right, and that's where at some point I think I've probably talked about, if not in here, I've talked about it in another class. Most of us have gone on to either Apple's website or Dell's website and configured the most expensive server we can build. We've all done that at some point, probably.
Many
Okay. How much RAM can I put in this, and how many processors, and all this other jazz, right? Okay. Have a good Thanksgiving, Ian. So in any case, he has the bail. More important things to do.
No, I was thinking.
Your scared him off.
Oh no! Almost scared me off.
So in any case, so we've all gone through that. But does anybody really need the highest, latest, greatest Mac Pro with 64 gigs of RAM and 12 processors with 24 logical cores? Is that going to get us? Is that going to get us anywhere?
I just wanted to watch Netflix.
Huh? Oh,
Yeah.
okay. Well, yeah. So
It's
what do we
32
use our computer for most of the time? Netflix or
Emails.
playing a video game that's only going to be able to use 2 or 3 of those cores at once. All right, so people drop $13,000-$14,000 on your maximum build, right? And so who would get their money's worth out of that?
Well, in theory, a computer like that will have a longer end life.
Why?
More power to keep up with system updates and that. Provided
Not really. Each individual core isn't necessarily faster than an individual core in another machine.
Mm-hmm.
So if you can only run two or 3 things at once anyways.
No, I meant like software-wise. Like as a newer operating system comes out or something like that, and it's heavier on the hardware.
Oh, right. But just because it's heavier on the hardware, it's going to benefit more from having 4 faster processors than 24 slower ones. Because it's not going to use 24. It's going to probably not use 4. is the issue. So you mentioned graphic design, so probably not the actual design part of it. It's probably going to be more the rendering stuff.
Yeah.
Video rendering, I think I usually use the example of video conversion. Okay, so if you're somebody who steals a lot of videos off the web,
My buddy does.
okay, and you need to convert it to the format for your Roku or your Apple TV or something like that, okay, a hour and a half long video clip. Right, an hour and a half long video clip. That guy might take on a let's take a laptop. So this is a pretty decent laptop here. An hour and a half video clip might take 45 minutes or something like that to convert on this machine. We took it down to the Mac Pro we have in the advanced lab or whatever down there. It would probably take 2 minutes to convert that same video because it's not because the machine. If you're on that machine and you're using Xcode, it's going to feel the same speed as this, okay? If you're on a MacBook Air, okay, you're on this guy, and you're checking email, it's not going to feel any slower than that $10,000 computer down there. You're not doing something that's using the hardware. You're checking email, all right? But now if you take a task like video conversion, which is infinitely divisible, that's the nice thing about rendering video or video conversion or rendering graphics is you can literally divide that up as many times as you want. So now we can take advantage of all 24 logical processors. So it will literally take maybe not 1/24th of the time, but maybe 1/22nd of the time. And it's going to be a little overhead for kind of managing all the multiple things, doing stuff, and then bringing them back together. But
thing literally has 24
I think we have dual quad cores in there. So I think it has 8 physical processors, which each have hyper-threading. So technically 16 logical cores in that one. I think the biggest one you can get from them right now is a dual 6-core that has then 24 logical cores. But whatever. The punchline is only very specific applications can take advantage of all those cores. Having more cores isn't any better if you're playing Minefield or something. Is that the game on the PC? No, not Minecraft. Minefield.
Yeah.
Minesweeper. Have you guys seen the YouTube video? That's like a thing of that. It's yeah.
I have not seen this.
Yeah, it's pretty funny actually. Huh? Yeah. It's like they would.
You can't just talk about it and not show it.
You look to the left, you look to the right. It's mine. And then there's another guy. One of the guys blows up because he put something. I mean, it's not like crazy hilarious, but it's entertaining.
This fairy tale?
Huh?
Yeah, best thing ever.
Yeah.
I'll let John see anything. That's the best thing ever.
No, but it was funnier than I expected. But I especially got hooked on his. That was it. That is part of his theme song.
Like hype.
That one part of the theme song. I was practicing that sound over and over again.
That's
My
like
wife-
a Hispanic thing, you know that, right?
Yeah,
Huh?
it's like
That sound like all the Hispanic.
No, I get it, but the person doing it aggressively for that exact little period of time. I had a teacher years ago for some history class, I think, and he was not Hispanic. He was very much like probably from Illinois, right? Somewhere. And he couldn't say the word conquistador without rolling crazy R's. Conquistador. I mean, it was crazy. That wasn't even an exaggeration. I may have not done it justice. Okay, is what just happened. Huh?
every time.
Every time he'd say it. Yeah, I mean,
That was
and
probably fun.
I would have worked my pants.
yeah, it was funny. So in any case, we might have various scheduling algorithms depending on whether something's in the foreground or the background. So scheduling has to be done between the various queues. We have a foreground and a background queue, and then maybe within the foreground queue we have priority queues, and maybe even the background queue we have priority queues. So we might have fixed priority scheduling, serve all from the foreground, then from the background. That might be reasonable if we assume that background processes are always less important than foreground processes. Some things that we can assume belong to the operating system might be important and might not necessarily be low priority, yet they are technically in the background. So that's a coin flip. But we have, in any case, just like we have with priority scheduling before, we still have the possibility of starvation. If we're always going to give special treatment to the higher priority processes, paying no attention to any other variable, we might starve out some processes depending on, how often things are entering the system. Right? If we always have important people getting in line at McDonald's cutting to the front of the line, the steerage at the back of the line are never actually going to make progress towards the front of the line. And they get starved. All right? That's starvation. So we can use time slice. Each queue gets a certain amount of the CPU time. So we might decide that the highest priority queues maybe get 60% or 70% of the CPU time. Okay, but the other queues are still going to get some CPU time. Okay, we'll schedule them, just not as often. That will buffer against starvation, right?
So is there a difference between time slice and time queue?
Time slice and time queue. Where's time queue?
Quantum.
Quantum, yeah.
Time slice.
No,
time
they're the same.
Okay.
Yeah, that's just how much time are we going to allocate on the CPU for it. Quantum just sounds cooler and
More
difficult and scientific-y.
I'm going to use quantum.
And usually it's in bold. When we say time quantum, it's a thing. So in any case, these are all like little tricks we might do to minimize starvation. Again, we're rolling the dice, right? Because every person might use their operating system a little bit differently, although there's probably patterns within humans in general. All right, so picture of what we just talked about. Look at the student processes of the lowest priority.
Story of our lives.
Multi-level feedback queue. A process can move between the various queues. So possibly through aging. Longer something's been in the system, we bump it up in the queues. So it could be defined by the following parameters. We have a total of how many queues, how many levels of priority we're going to have. Which scheduling algorithm are we going to have for each of these queues? Do we handle different queues differently? So a couple slides ago, we talked about maybe the highest priority queue is handled in a round robin sense. We're going to leverage the idea that our CPUs are fast. So one thing we want to kind of pull out of that is round robin tends to be the one that's most compatible with real time, the end user experiencing it. So when we have things in the foreground and it's the highest priority because they're in the foreground, applying some derivation of the round robin scheduling algorithm probably makes a lot of sense, especially today, seeing as our CPUs are so fast. All right, so we'll give them high priority. We'll give each one a little bit of CPU time. And actually, with a quad-core CPU, we can give 4 of them CPU time simultaneously. So that round-robin thing becomes even more interesting, right?
Maybe.
You're getting CPU time. Well, if they're separate processes, they're not related on each other, not related to each other. Now we're not dividing up labor. Now we're saying Microsoft Word is running on one core while Instant Messenger is running on another core. 2 separate applications. Right? So that is, by definition, division of labor, unless these guys are related to each other for some reason. So now we can actually give them CPU time more often for a longer period of time or for the same period of time. So now, in the big scheme of things, within a 1-minute period of time, they're getting substantially more CPU time than they would get on a single or a dual core system, just because of how round robin works. Go ahead.
So just like as a general question, if I'm sitting at home playing on my desktop and I launch Fallout 4, and then I go to like the task manager, and you can set the priority of that in like the processes.
Mm-hmm.
If I set that to high or real time, like I've done that and not done that, and I can't tell any difference. Do you think that you should be able to tell a difference, or do you think that would have an effect?
It technically will have an effect. Whether or not you'll tell the difference is the whole separate story. It depends on what else is happening on the system, and then whether or not you're experiencing the other things happening on the system. Because if you're playing Fallout, it's going to be in the foreground, so already by definition, it's going to have a high priority. Okay, so all you're doing is you're basically saying, give this guy the absolute highest priority. Only let other guys have access to the CPU if they absolutely have to. Machine will reboot unless this thing gets CPU time soon. So punchline is you probably have a fairly fast processor. So if that's the case and you have lots of cores and all that stuff, it's already getting a lot of CPU time. So a lot versus a lot plus 1 might not be discernible by you. Let's see. So we have various scheduling algorithms that we might use for each of those queues. We might have various methods that we use to determine when we upgrade a process. That's the whole aging thing, or maybe we have other ways of upgrading a process. So for instance, he just said, well, I could just go in and manually say this guy's more important. Process got updated. User said, I want this guy to be important. All right. We could also choose when do we demote a process. So for instance, maybe something that used to be in the high priority queue hasn't really moved into the foreground for a long time. So maybe we bump it down a couple of notches or something like that, so it doesn't get CPU time that the user isn't benefiting from. Let's see, method used to determine which queue a process will enter when that process needs service. It's all the same crap. It's just saying, if you need to get the CPU, what queue do you need to get into that has the highest likelihood of getting CPU time? It's stupid. They might as well have that in a dumb picture. This is what we just talked about. Multi-level stuff. We could have various time quantums within our queues. So things that are up here maybe get a shorter time quantum because they're in round robin. So we're not going to give them as much time on the CPU, but they're going to get more total time on the CPU. But again, this has to take into consideration context switching. Okay, maybe these guys, this may be more of a batch processing thing or something like that, or kind of a middleman thing. We're going to give them a little bit more time on the CPU with the understanding that they're probably not going to get the CPU as often. So now when they do get the CPU, let's give them a little more time on there. And then these will be our batch guys down here where look, whatever your time quantum is. And actually, first come, first serve, arguably this could be literally let it run until it doesn't need it anymore. We're not even going to kick you off based on time. You run until you need I/O or you're finished. And especially today when we have multiple cores, we might have a core that sits there not even busy, and this is no big deal. Okay? So, now, we kind of already talked about this in the previous chapter, that there really isn't huge differences between threads and processes other than who owns them, and where they live most of their life. But even last chapter, we talked about how threads sometimes have to escape the parent process to do some kernel level stuff or get some extra CPU time. All right, so distinction between user level and kernel level threads, talked about those. When threads are supported, whatever that means. So none of that's even applicable. It's just stupid. Many to one, many to many models. We talked about those. Thread library schedules user level threads to run on LWP. I don't know what that guy stands for. We'll find out in a second. Known as a process contention scope. Oh, that's just a fancy schmancy word, isn't it? So this guy is likely, we'll see where this is going, but I'm going to make a guess here that the process contention scope is a fancy way of saying that every process that has threads is contending for the same thread-based CPU time for its threads. So these guys are competing with each other. So we're going to treat processes that are CPU bound that also have threads in kind of a different category than we'll treat other processes that don't have threads. Because now those individual threads are going to be competing on CPU time. So two processes might be more like scheduling 12 things. A programmer can set the priority of their threads, but most of the time you just choose default threads. Kernel thread schedule onto available CPU is system contention scope. Okay. So these guys are all competing with threads in the system, but there still has to be a priority amongst the process that own that. P-thread scheduling. API allows specifying other the contention stuff. So this is process contention. This is scope contention during thread creation. A p-thread scope process schedules threads using PCS scheduling. So a p-thread scope process allows the processes to compete for when their threads get CPU time, where a p-thread scope system allows the threads to compete for when they get CPU time. So instead of having a layer of abstraction where the process houses threads and the process is fighting the battle for their child threads, we can have the threads all fight their own individual battle in the pool for getting CPU time from all the other threads in the system. So we can make an argument where one of these might be better than the other one, but it's still going to be a crapshoot. All right, this is dumb. All right, so this is where things get interesting again, though. So multiple processor scheduling, we've already been kind of talking about this a little bit, or at least alluding to it, where when we have more than one processor that we're now scheduling for, more than one resource that we have available to us that we can have things run on, we have more power, but with great power has great responsibility. So, right? So, Christian worldview?
Spider-Man.
Really?
Yeah.
Same thing. You don't think Spider-Man goes to church?
I think he does actually.
Christianity exists for sure.
See?
Yeah, for sure it does.
Yeah.
I don't think he does, because probably last time he was in one.
Well, that's the thing
you
with
know,
Captain America.
I
Is
don't-
he's friends with a god, Thor, and I don't know, something else. I read some meme on it that was like that. But he's friends with a god, but he's still Christian.
Yeah, see? That's definitely a Christian
Double
worldview.
Christian worldview.
Yeah. He actually knows, I mean, well, he knows somebody they call a god, but he's just,
He's pretty much exhibited the traits of a god.
Well, right, but he's essentially just a leader of a you know, the of the Asgard, and he happens to have some pretty impressive powers, right? You know, that doesn't make him God. You know, let's take, you know, Thor versus Jesus, who wins?
Well, I mean,
That's Christian worldview.
I want to see that movie. Right to Marvel. You need to make this.
So what if that? What was that? What if that was like a WWE like Super Slam event or something like that? The hammer hits the ground. Jesus walks up, just picks it up like it's nothing. It's like, Thor, he's just look of shock.
it'd be an episode of Deadliest Warrior.
That would actually be a pretty good show.
They need to do that on Celebrity Deathmatch.
That show's not on anymore, right?
No, I wish it was. Some of the dumbest show.
The claymation stuff.
Yeah.
Okay, so multiple processor scheduling. Things get more interesting with this because now we need to kind of have a quarterback that decides not just who gets the CPU next, but who gets which CPU next. All right, so things get more complicated because now we might have two processes that say they're ready for the CPU, but what if they conflict with each other? What if one has to happen in a certain order relative to the other one? Where do we put that onus? Who gets to decide? Who's in charge of that? Do the processes themselves kind of communicate and only get into the ready queue when they know it's safe to get scheduled? Or do the processes leave that up to the quarterback, and the quarterback somehow has to know that, okay, well, I can't throw to this guy because this guy needs to catch a pass first. And the quarterback thing's breaking down a little bit, but whatever. Punchline is things might have to happen in a certain order.
Do processes have the ability to switch priority queue, or is that the scheduler that would do that?
The scheduler would have to switch them. Now, a process could request a switch, especially like in your situation where you said, the user has asked a process to be a higher priority. So the question, are you talking to the process and the process is making the request on your behalf? Or are you talking to the scheduler and the scheduler is going and finding the process you're talking about? I'm not sure it matters, but, you know, let's see. Structures. All right, so symmetric multiprocessing, each processor is self-scheduling. All right, so every single processor is going to have their own schedule. We're going to swing back up on these here in a second. So each processor is self-scheduling. So all processes in a common ready queue, and each has its own private queue of ready processes. So this is currently the most common thing, but this is also probably not the most ideal. Because now what you have is you have two separate processors, let's say, in a dual core system, and each one of those guys is going to be feeding off. So we have a common ready queue, or each has its own private queue of ready processes. So let's look at the two different those two different models. If we have two processors grabbing from a common queue of ready processes, okay, it's like a Pez dispenser, right? Okay, they're just grabbing whatever's on top of that stack, whatever's at the front of that line, and dealing with it. That's going to make the assumption that those processes are only in that ready queue if they're actually ready to have CPU time and won't conflict with each other. Because in that particular case, the part of the operating system that we've said has to be really, 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 really fast, that CPU schedule, the short-term scheduler, it's not going to be asking a whole lot of questions. It's going to grab the next guy from the queue, pull it into the CPU, and if there's a conflict, it's not his problem. All right, so those guys would have had to get in line with some knowledge about whether they can actually get CPU time or not. All right, so that's symmetric multiprocessing, as opposed to, and we'll just finish with this comment, we'll leave it on this slide, as opposed to having symmetric multiprocessing when we have two independent ready queues for the for each of those two CPUs in a dual core system. So now these guys, when they go to get in line, they have to choose the shorter line, maybe. Something like that. All right. So maybe a question might be, what's the advantage of that versus the first one? Well, it could be a race condition if they're both trying to grab the front of the same queue at the same time. we separate the queues, we kind of take that out of the equation, but maybe put a little bit of additional overhead someplace else. All right, have a good break. I will see you on Monday.
No, you'll see me later today.